Module 3, multi-level caches. So this is another very important topic. But a lot of material of this part comes from Appendix B. Otherwise you may not be able to find it. Appendix B. Actually, most of the material comes from Appendix B. A small amount, related from Chapter 2. All right, and we only use this part, Part C. After only use this module. Module 3 for this cache topic. After Part C, we will complete this topic. Then after this one, I plan to use 2 parts to do problem sessions. So mainly help you solve homework assignment number 1. So there are many questions. Some of the questions relatively hard. So I like to give you some hints or some, sample questions, more example, more explanations. All right, so let's start Part C first. C.1, Introduction to Multilevel Caches. First, so let's look at the current problem we want to solve. So there is some problem not quite good for the current situation. So that's the how to reduce miss penalty. If you look at the miss penalty, when you have a cache miss, you have to go back to the main memory to load that cache block, and the penalty, you need to pay the penalty. The penalty approximately 1 to 100. So 100 times of the cache hit time, approximately. Not exactly, but in that range. That is too big. That is, too large, the cache penalty. So we want to reduce that number. So the question is there any way we can reduce? So that's the topic of this part. All right, so the problem in cache memory. When a cache miss occurs, we need to pay a high miss penalty. So approximately 1 to 100 ratio. All right. The question, is there any way to reduce the high miss penalty? After this topic, so you will see there is a very good solution. The idea is pretty simple, but the result is really, really good. What is the cause of the high miss penalty? So if we know that cause, we can find a solution. The cause is typical main memory capacity. The current computer, the typical main memory capacity, certain number of gigabytes. Here, from typical this main memory. So you can see in our current computers, usually several gigabytes. Some of the machine you can get, double-digit gigabytes for main memory. But at least several gigabytes, right? So in that capacity. But if you look at the cache capacity, in the range around megabytes, certain number of megabytes, or even sometimes smaller than 1 megabyte. It could be smaller than 1 megabyte. then you can see how much is the gap. The gap usually greater than 1,000 to 1 ratio. Giga, mega, 1,000 to 1. But, the multiple of gigabytes, that number usually much larger than the multiple of the megabytes. So you have, several thousand to 1 ratio. That gap is really big gap. Yeah. So the high cache miss penalty is due to this big gap in memory capacities in these two different levels of memories. That's the main reason. In order to find a solution, in order to, get a better overall performance, there is a straightforward idea. Reduce the gap. Okay, yeah, all right. How to reduce the gap? Yes, how to reduce the gap? Add another level of cache. So multi-level cache idea comes out, obviously, with this kind of analysis. You can understand we should use multi-level caches. Okay, all right. Then, so let's go a little deeper along those multi-level caches. So when we do multi-level caches, we need to understand for different levels, their roles are quite different. We need a fast performance. When we fetch cache block in a cache, we want fetch time, hit time, fetch time very fast. So we like to use high-speed cache, but we know the high-speed cache, first, the capacity cannot be too big. If the capacity is big, so that will make the fast access harder. So, but another thing is, if you want the very fast access, but you also want to increase capacity, that will be very expensive. The cost is also another big issue. So we need to control the cost of the whole system, the machine design, whole system. The cost is a big factor. All right, so high capacity cache, because right now you have two levels. Let's think about two levels. One level, you emphasis on the fast speed. Another level, then you emphasis on high capacity. So you can also take care of the high capacity part, but the high capacity cache usually relatively slower. So the fetch time, performance will be slower. Because you want to control the cost, right? You want to control the cost. If the cost you make it, using the faster technology, it will be too expensive. All right, so now in order to build a system, first you want to have faster overall performance. Second, you want to control the cost of the whole system, not too big. You want to both. So you want something, balanced. You want to balance all those important factors. So then the solution is cache hierarchy. So we call cache hierarchy. Multiple levels. Top, bottom, the pyramid shape type cache hierarchy. But here we only talk about the cache part. We saw memory hierarchy before, right? 4 levels memory hierarchy. Now, we split the cache part in multiple level cache hierarchy. Yeah. So that's the solution. So that's the idea. Yeah. All right, so next, let us just look at a 2-level cache. Yeah. Because the idea, the principle, the method, the same. So we only need to look at a 2-level cache to understand the whole idea. Yeah. All right. Yeah, the diagram like this. Between CPU, main memory, we insert 2 cache levels. L1 cache, we emphasize on high speed part. So its capacity smaller, excess speed much faster. Yeah. So the cost not too high. So we control that part. Cost not very high. Then L2 memory cache level. Yeah. So this one we wanted the capacity a little larger so we can reduce the miss rate. Yep. When the capacity larger, the miss rate can be reduced. Cache miss. Yeah, that's important. Yeah. But in order to control its cost, so we cannot use, the same fast speed type of material technology of L1 to build L2. Yeah. Should be different. Yeah. Cheaper material technology than L1 way type. Yeah. Then we can make the whole system with pretty good performance, but the cost is not very high. That's the goal, our design goal. Yeah. All right, so with that, it's a trade-off in cache hierarchy. We need to make some trade-off. So we sacrifice something a little bit, right? So here, so we sacrifice capacity a little bit in L1 cache. And the L2 part, we sacrifice performance a little bit. So the trade-off. So increase here a little bit, decrease there a little bit. Yeah, so we get a very good combination, a balanced solution in this way. Yeah. All right. So the solution is adding another level of cache between the original cache and the memory. So in this way, you can see the gap will be reduced. The gap between main memory and L1 cache will be reduced. The gap is not that, multiple thousand to, something. Yeah. All right. Yeah. Then the first level cache can be small enough to match the clock cycle time of the fast processor. The processor speed very fast, so we want the hit time of L1 cache very fast, matching the clock processor speed. Otherwise, the processor has to wait. So when fetching some data in the cache, the processor has to wait because it's too slow. Yeah. So try to match the speed of processor. Then the processor does not need to wait long. Yeah. Just can get data quickly. Yeah. All right. Then the second level cache can be large enough. So we emphasize the capacity large enough to capture many accesses that would go to main memory. That's the miss penalty. Otherwise, if you do not catch a lot of cache misses, then you have to go to the main memory and suffer extremely slow performance. All right, so thereby lessening the effective miss penalty. Effective, the real miss penalty. So we have that concept. Effective miss penalty, lessening, yeah, reduce, make it weaker, like that. Yeah. All right. So later, you will see what's the meaning. So when we talk about the formula, memory access time formula for multi-level caches, then you can understand this. What's the meaning of this lessening the effective miss penalty? Okay? Yeah. All right. So that is the multi-cache board, Yeah. So you get an idea in a typical computer system. Yeah. All right. So next, in order to give you good impression, I like to use some, example to show you the impact of the multi-level caches. Yeah. All right. So in this example, the main memory access time in main memory, 50 nanoseconds. Okay, 50 nanoseconds. Yeah. All right. So then we have some other numbers. L1 cache, hit time 1 nanosecond, very fast. Okay, 50 to 1 ratio. So you get it. So that difference is pretty significant. And 10% miss rate. So this number relatively high, 10%. Although you may feel it's a not big number, but what I said, relatively high. Comparing with other much lower miss rates, this is relatively high. All right. Then we put an L2 cache. Now the hit time 5 nanoseconds. So much bigger than L1 hit time, 5 to 1 ratio. Okay, 5 to 1 ratio. But the miss rate much lower, 1% miss rate. So you can see also, we sacrifice at the hit time part, but we significantly reduce the miss rate. So that's worth it. Yeah. The trade-off issue. Yeah. L3 cache, 10 nanosecond. 10 nanosecond. You can see, another 2 to 1 ratio, 5 to 10. But the miss rate much lower, 0.2% miss rate. How good it is. All right. Now, so let's put things together and we do comparisons. We compare the overall memory access time. All right. First, no cache, just access directly from main memory. AAT, what's the AAT? Average access time. So this AAT, average access time. Okay? Access time. Yeah. We talk about the average memory access time before, right? We have formula for that. Average memory access time before. Okay? Here, AAT, average access time. 50 nanosecond. The slowest case. Second, we just use L1 cache. We only use L1 cache. So by our average memory access time formula, you can see the number is reduced from 50 nanosecond to 6 nanoseconds. Pretty big reduction, right? L1 cache, you reduce from 50 to 6. Next, L1, L2 cache. Yeah, so you combine L1 through 2, 1 through 2. So two level caches. Yeah. This time you reduce the average memory access time from 6 to 1.55 nanoseconds. Another significant reduction. Yeah, almost 4 to 1 ratio. 6 ns to 1.55 ns. Okay. Next, L1 through 3 caches. This time, reduction a little bit, but not significant. See, 1.51 nanosecond. only the second digit after the decimal point from 1.55 to 1.51. Not that big, right? Not that big. Yeah. The reason is simple. The reason is simple for this example because the gap is not that big. Now, after we put a two-level caches, we can reduce the gap pretty big, so we do not need to add a L3 cache. We do not need that. Even you add an L3 cache, you cannot improve much for this example. But if you have some example, the gap is much bigger. Yeah, the gap between main memory and the L1 cache much bigger than this one. Then you have chance to reduce more using L3 cache. So that's another reason. Two-level cache, most popular. Two-level cache, most popular. The three-level cache is only for big system. So what I mean, most popular for our, usual system. It's really already very good. This kind of access time already really good, right? Yeah. Only for much larger system, so then you may need to use the three-level caches. Yeah. All right, so we finish this C.1 introduction part.